The next quantum number has got a long name, the orbital angular momentum quantum number, and it's given a lowercase l here, and usually they'll write it as a script L because lowercase l looks like a numeral 1 in text sometimes. Now what does all this mean? Why such a complicated name? Angular momentum has to do with how a spinning body tends to maintain its axis in the same place. So if you take a top and you start it spinning, the top will stand up on the point because it will resist having the angle that its axis is at changing. If you take a bicycle wheel, so here you got a bicycle wheel and you spin it. So you get this spinning really fast, and then you hold either end here, and then you try to twist it. You'll feel really strong resistance to it twisting off of its axis. And this is really what keeps you up on a bicycle. You may notice that this effect, its resistance to having its axis twisted, is stronger when it's spinning more. And when you slow the bicycle down, you get a little bit wobbly. It's a little bit easier for the wheels to spin at a different angle. So angular momentum refers to the tendency of something that is spinning like this to stay pointed in the same direction. There are devices like this, gyroscopes they call them, in the bottoms of ships. They're great big wheels that are spinning, and they will tend to keep the ship upright even if the waves are trying to make the ship toss and turn. Alright, so that's where that name comes from. It turns out with electrons moving around an atom that they have some angular momentum associated with them as well. And it happens to be quantized. So there are only certain values of the angular momentum that are allowed, and no others. So the orbitals have a quantized angular momentum, and this is the quantum number for that. So kind of a long story, but that's where that long name comes from. Now, what's the significance of it? If you label a wave with L, what does it mean? L determines the shape of the orbital. Now the orbitals we've drawn so far have been spherical, but you can have other shapes with this. When you have L equals 0, that means that there are no nodes through the nucleus. So that would be like the waves that we have seen up until now. If you've got your nucleus here, and you've got your cloud around the nucleus, and it kind of thins out the farther you get away from the nucleus. This would be an example of a wave with L equals 0. Now, what happens when you have L equals 1? There's one node through the nucleus. So here's my nucleus. Now the node is going to look like a plane. I mean, if I was going to draw it like in 3 dimensions, I draw like maybe a little sheet here. Really, it's kind of infinite, but I'm going to draw it like that so that you can kind of see that there's a sheet and the nucleus is in the center of the sheet. And then on either side of the sheet, you're going to have a cloud. There's another one behind here. So when you have L equals 1, it's going to look like that. Now, let me draw it another way. Let me draw it so that we're seeing the sheet edge on. So there's the node. And then if I'm looking at these two clouds, they're like two lobes. going to look something like this. So you have these two clouds on the either side. If you want to draw these things as surfaces, you can do that too. That's a little bit easier. Imagine you've got a spherical surface around here for this one. It will look like that. And this is, think of this as a holder. It contains most of the electron's charge. And what would the holder for this one look like? Well, here you got your nucleus. Here you have your node. And you could draw a container for this cloud on this side and a container for this cloud on this side, with a gap between them where the node is, because the cloud cannot touch the node. There's no negative charge along the node. So these are two different shapes, and you can see that if you change the value of L, because you're changing how many nodes go through the nucleus, you're changing the shape here. Now these shapes have names. This shape is called an S. So people will call this an S orbital. This shape also has a name. It's called a P shape. And they'll call this a P orbital. And whenever you have L equals 1, you have P orbitals. When you have L equals 0, you have S orbitals. Now, are there other shapes? Yep. If you have higher values of L, you're going to get other shapes. Let's look at a couple. If you have L equals 2, you're going to have two nuclear nodes. Here's the nucleus. Let's draw a node cutting through the nucleus here and a node cutting through the nucleus here. Then the clouds are going to be where the nodes are not. So you're cutting the cloud into 4 pieces. So you get this kind of cloverleaf shaped cloud, and this is called a d orbital. Whenever you have L equals 2, you'll get a d orbital out of this. And this is one way to cut it. You need 2 nodes. Now there's another way to cut it with nodes. Instead of having 2 planes, you can have 1 cone. Here's what a conical node looks like. Here's your nucleus. So these things are cuts. This is like a one-dimensional cut with a knife that way, a one-dimensional cut with a knife that way. And then that's your 2 nodes through the nucleus. This one is considered just one. So imagine you've got a knife and you're cutting, and it's like you're twisting the knife, you know, around in a cone. And this is a 2-dimensional cut. So it counts. Now when you cut the cloud like that, you'll get an orbital that looks like this. There's a cloud in the cone, and then there's a sort of a donut that goes around the edge, around the outside here. So you get an orbital that looks like that. If I want to draw these both as surfaces, I can draw this one like a clover leaf kind of thing. You can draw it like this. That's one way to draw a d orbital. And then there's a special d orbital that looks like this. So this is another d orbital that you can have. It's got a kind of a donut around the middle. So it looks kind of like that. These are both d orbitals. They're both orbitals with L equals 2. What about L equals 3? Well, things get more and more complicated. Let me just draw a really simple one. Here's the nucleus. Suppose I do 3 planar cuts. So I did 3 cuts through the nucleus. I'm going to get a cloud here, 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 and a cloud here. That is one way to do it. That is one of that is one orbital that looks like L equals 3. This is called an F orbital. It's got 3 cuts. Now you could do a conical cut. So suppose you do a cone, cut a cone, and then do a plane cut across the middle. And what are you going to get there? That's 3 cuts, because the cone counts for 2 cuts because it's two-dimensional movement of the knife here. And then this is a flat cut, so that counts as 1. So that would be L equals 3 as well. Well, let's see. Put a cloud every place where there's a space. You're going to have a donut on top here and a donut below that cut. So let me see. Let me draw both of these over here. You can have something that looks like sort of like an asterisk kind of thing. Here, I should put the nodes in. And then draw around that. So this would be one F orbital. And then this would be another F orbital that you could have. It's got a donut there, and then another donut here, and then a lobe that goes down that way. Now these have, sometimes these orbitals have names depending on how they're oriented in space, and you don't have to know them. This one happens to be a DZ squared orbital, they call that. And this one they call it an FZ cubed orbital. And these can have names like DXY or something like that. So the different shapes that these things can have different names. Now what do I want you to know? Get this table in your head, because we're going to need it. From the value of the L quantum number, I want you to be able to write down what the shape is that goes with that. And sketch the shape. How about, you don't have to do the F's because they get kind of complicated. But how about you be able to sketch me an S, P, and a D orbital. An S orbital looks like a nucleus with a sphere around it and no nodes. A p orbital looks like a nucleus with a node through it, and there's 2 lobes. Both are the same orbital. It just has 2 pieces. And a d orbital is a nucleus with 2 cuts through it. Looks like a clover leaf. Sphere, dumbbell, clover leaf shape for these. And then the F's, they're more complicated. They've got 3 cuts, 3 nodes that go through the nucleus with them. But these are the important ones that you should know. Now, how does this L quantum number work with the principal quantum number, the N quantum number? L depends on N. So L can take on these values. It can start with 0, and it can count up by integers to n minus 1. So L must be less than n, because the highest value of L that you can possibly have is n minus 1. So let's list all of the L values that you can have for different shells, okay? The smallest value of n that you can have is n equals 1. What are the values of L that you can have with that? Only L equals 0. That's the only possible value of L that you can have in the first shell. That is the place with n equals 1. What about n equals 2? Well, let's see. We can go 0 to 1. We can only go up to n minus 1. n minus 1 will be 1. So we can have 0 or 1. So in the second shell, we can say that is with electrons with n equals 2. you can have two values of the L quantum number, the orbital angular momentum quantum number. You can have L equals 0 or L equals 1. What about N equals 3? Well, what's the biggest value of L that you can have? It'll be N minus 1, so it'll be 2. So you can go L equals 0, you can have L equals 1, you can have L equals 2. What about N equals 4? What values of L are you allowed to have? Well, 4 minus 1 is going to be 3. So you can have L ranging from 0 to 3. Now, this gets kind of clunky, right? Listing all of these L values. Let's name these situations. I'm going to introduce what I'm going to call subshell notation. So we called things that had the same value of N shells. We're going to call things that have the same value of N and L subshells. And to do a subshell, you're going to take the N value, here it's 1, and then you're going to take the shape code for L. Now, when you had L equals 0, what was the shape code? S. So we would say this is electrons that have N equals 1 and L equals 0. We'd say that they were in a 1s subshell. Okay, let's name these other ones. What would you name this one? You take the N value as a number, and then you take the L value as its code. L equals 0 is S, so that would be a 2s subshell if you had N equals 2 and L equals 0. And here you could have, what's this one? L equals 1 is a P, so you could have a 2p subshell. So it's not possible to have P-shaped waves, L equals 1, in the first shell. The p orbitals, the ones that look like dumbbells, only appear in the second shell, and shells that are higher than that. Okay, let's do these. Here you have N equals 3, so this will be a 3s subshell, right? Because L equals 0. This will be what? 3p. What'll this be? Now, when you have L equals 2, we said before that you have D. So this is a 3D orbital. So notice that you only get these D waves, these cloverleaf-shaped waves, when you're in the third shell or higher. There are no D waves. There are no D orbitals in the first and second shells. And finally, let's look at fourth shell. Here you have N equals 4 and L equals 0, so you have a 4s there. Here you have N equals 4 and L equals 1, so you have a 4p subshell here. Here you have N equals 4 and L equals 2 is a 4d subshell. And here you have N equals 4 and L equals 3. And what did we say that was? We said L equals 3 is an F. So we have a 4f subshell here. So, test question. How many subshells are in the third shell? 3. There are 3 different subshells. How many subshells are in the second shell? 2. How many subshells are in the fourth shell? 4. Do you see a pattern there? Every shell contains whatever n is, number of subshells. So there is 1 subshell in the first shell. There are 2 subshells in the second shell. There are 3 subshells in the third shell. And there are 4 subshells in the fourth shell. How many do you think is in the fifth shell? There'll be 5 subshells in the fifth shell. How many in the eighth shell? There should be 8 subshells. But what happens when we go up above 4 with these letter designations? Well, if you had an L value that was higher than 3, what would you call it? Well, they start to go in alphabetical order after that. So after F, they'll go G, and then 5 would be an H. So you can name orbitals in those higher shells. But the thing is, we only know atoms, we only have stable atoms that have S, P, D, or F waves in their ground state. So we don't know any ground state atoms that have G orbitals or H orbitals in them. So you don't have to worry too much about these. Know these first ones, because these are the ones we're going to have to use. So there's a definite pattern here that you can start to see. All right, we'll look at the next quantum number, the last space quantum number, in the next video.